Hello everyone, welcome to this lecture. The plan for this lecture is as follows. So, in this lecture we will introduce prime numbers, we will see some properties of prime numbers. We will also discuss about the Naïve algorithm for primality testing, which is a very interesting computational problem, and we will discuss about GCD and Euclid's GCD algorithm. So, let us start with prime numbers. So, the definition which all of you are aware of. So, we will say an integer p which is greater than 1 is called a prime number if the only positive factors of p are 1 and the number p itself. Okay. Whereas, if the number p is not a prime number, then we call it as a composite number. Okay. It is easy to see that all prime numbers except 2 are odd, because if you consider an even number, 2 is always a factor of that even number. Okay. But 2 is not a prime number, because the only factor of but 2 is a prime number, sorry, but 2 is a prime number because the only factor of 2 is only factors of 2 are 1 and the number 2 itself. Okay. So, in some sense except 2 all the prime numbers are odd, but we do have an even number which is also prime, namely the number 2. So, you can consider 2 to be an odd prime. It is very odd, that odd in the English sense, it is a very odd property that you have an even number, but it is still a prime number. Okay. Right. So, we know some interesting we know some nice properties of prime numbers which we had already discussed in this course. So, we know the fundamental theorem of arithmetic, which says that you take any integer greater than equal to 1, it can be written down uniquely as product of prime powers. Okay. And we had also, so how do we prove this? So, we proved it using strong induction when we discussed proof by inductions, and we also know that there are infinitely many primes. So, we saw there are several proofs for this, but we discussed one of the proofs in this course earlier. So, these are two interesting properties of prime numbers which you should keep in mind. Now, the next question is how exactly we check whether a given number is a prime number or not. So, I will be discussing the Naïve algorithm which many of you might be aware of. So, the algorithm uses the fact that if at all your given number p is a composite number, then it will have a divisor which is less than equal to the square root of that number. Okay, and the proof is very simple. So, let p be a composite number, and since p is a composite number, it will have a factor, say a, and the factor will be definitely greater than 1, because the definition of composite number is that it should have at least one factor different from 1 and the number itself. So, the factor a will be greater than 1 and less than p, and then since a is a factor, I can say that there is a b such that a times b is equal to p. Okay, that means b is basically the b is basically p over a. Okay. So, now the claim or the theorem statement here is that either a is less than equal to the square root of p or b is less than equal to square root of p, and this can be easily proved using contradiction. So, on contrary, assume that a is greater than root p and b is also greater than root p, then this gives me a contradiction that a b is greater than p, which is not the case, because my premise says that p is equal to the product of a and b. Okay. So, based on this theorem, the Naïve algorithm is as follows. So, you are given input number p, you want to check whether it is prime or composite. You know that if at all it is composite, then it will have a factor within the range square root of that number. So, that is what you try to do here. You try to check whether it has at least, whether your given input number p has at least one factor I within the range 2 to root p. So, you range over all possible values of I between 2 to square root of your number and check whether the number I divides p or not. If you encounter any I, then you can declare that p is composite, but if none of the numbers 2, 3, 4 root p divides your p, then you can declare your p to be prime. That is a naive primality testing algorithm that you are aware of. Now, what is the running time of this algorithm? So, how many operations you perform here? So, there are root p iterations, and in each iteration you are performing a division. So, our measurement, our complexity measurement here will be how many divisions you are performing here to declare whether a given number p is prime or not. So, we will be needing square root of p number of divisions. So, you might be wondering this is a polynomial time algorithm, but that is not the case. So, imagine p is represented by an n bit number, then the magnitude of your square root of p will be 2 to the power n over 2, because your p could be as large as 2 to the power n. So, square root of p could be as large as 2 to the power n over 2. So, it might look like a polynomial time algorithm, but it is not. It is exponentially time, it is an exponential time algorithm, exponential in the number of bits that you need to represent your value p. So, again take the case when n is equal to say 1024 bit, okay, and say your p is as large as 2 to the power 1024 bit number, then basically you are your I is between 2 to something of order 512. That means, you will be basically performing these many divisions 2 to the power 512 divisions to check whether a given number p of 1024 bit is a prime number or not, and this is an enormously large quantity, it is not a small quantity. So, this is not a polynomial time algorithm. So, now you might be wondering that whether we have a polynomial time algorithm or not, and coming up with a polynomial time algorithm for checking whether a given number is prime or not had been a long standing open problem. People thought that we do not have any polynomial time algorithm, but in 2002 there was this algorithm proposed called as AKS primality testing, which is a polynomial time algorithm, polynomial in the number of bits that you need to represent your input number p, and this is called Agrawal-Kayal-Saxena primality testing algorithm, which in polynomial time can tell you whether your given number p is a prime number or not. Okay. Right. So, due to interest of time I will not be discussing the AKS primality testing algorithm, but if you are interested you can see the original paper. The paper title was Primes is in Pre. Right. Now, let us next define the greatest common divisor or GCD. So, imagine you are given two numbers a and b which are non-zero integers, and the greatest integer GCD of a and b is the greatest integer which divides both a and b. Okay. So, we say integers a and b are relatively prime, we also use the term co-prime if their greatest common divisor is 1. That means, so of course, 1 is a trivial divisor, a common trivial divisor of every a and b, but if 1 happens to be the only common divisor, or if 1 happens to be the greatest common divisor of a and b, then we say that a and b are co-prime or relatively prime. Whereas, if we have n values a1 to an and they are pairwise, we call them as pairwise relatively prime. If you take any pair of values ai and aj in the set of n values which are given to you, they are co-prime to each other. Okay. Now, an interesting question is, if we are given two values a and b, how exactly we find out their greatest common divisor? One approach could be that you use the prime factorization of A and B. What do I mean by that? So, as per the universal as per the fundamental theorem of arithmetic, A will have its unique prime factorization, namely A can be expressed as product of prime powers. So, let the various powers of the primes used in the representation of A are A1, A2, An and so on, and in the same way the integer B will have its unique prime power factorization. Then it is easy to see that the GCD of A comma B will be this value. But to use this algorithm, at the first place you have to come up with a prime power factorization of A and B, which in itself is a very computationally heavy task. Okay, so, we do not prefer to use this algorithm in general if A or A and B are very large quantities. Instead, what we use is we use Euclid's GCD algorithm, which is probably one of the oldest algorithms known. Okay. In fact, people believe that this is the first instance of an algorithm for any computational task, interesting computational task. Of course, addition, subtraction, they are also computational tasks and you have algorithms for that, but this is probably a very interesting computation, namely the computing GCD, and Euclid gave a very simple algorithm which we will be seeing soon. But to understand the Euclid's algorithm and why it is correct, let us first try to understand some properties of GCD. So, the first property here is that if your number A divides B and if the same number A divides C, then A divides B plus C, and it is very simple to prove. Since A divides B, then I can write B as some A times x, where x is the quotient and the remainder is 0, and C is divisible by A, I can say C is some y times A. Okay. Now, what I can say about B plus C? So, I can say B plus C is same as x plus y times A, and hence B plus C is completely divisible by A. Now, the crucial observation on which the Euclid's GCD algorithm is based upon is the following. Our goal is to find out GCD of A comma B, and for simplicity imagine A is greater than B, right. So, the idea that is used in the GCD Euclid's GCD algorithm is that if A is some q times B plus R, where R may be 0 if A is divisible by B, otherwise R will be something in the range 0 to B minus 1. So, if A is B times q plus R, then we can see that the GCD of A and B is same as the GCD of B and R. Okay. So, you start with A and B, where A is greater than B. Your goal is to find out the GCD of A and B. What this says is, what this statement says is that it is equivalent to finding the GCD of B and R. So, let us prove this statement. So, the proof idea here will be the following. We want to prove that the greatest common divisor of A and B and R are same. We will instead prove that every divisor of A and B is a divisor of B and R, common divisor of B and R, and every common divisor of B and R is also a common divisor of A and B. If we prove that, then that automatically shows that the greatest common divisor of A and B is same as the greatest common divisor of B and R, because we are proving this, we are actually proving a stronger statement. We are proving the statement about all common divisors of A and B, whether it is greatest or not. So, consider an arbitrary divisor D, which is a common divisor of A and B. So, since D divides B, it will divide minus B times Q as well, okay. And anyhow D divides A as per our assumption, and now I can apply this lemma, right. So, you have a divisor which divides one number and another number. So, the same divisor will divide the addition of the two numbers, and the addition of the two numbers here will be A minus BQ, and A minus BQ as per our definition is R. Okay. So, that means if you have a common divisor of A and B, then the same common divisor is is also a common divisor of B and R. On the other hand, assume that you have a common divisor D of B and R. We have to show that this common divisor D is also a common divisor of A and B. So, again we use a similar idea here, since D divides B, it will divides any q times P as well, and anyhow as per our assumption D divides R. So, again apply the same lemma. I can say that D divides the addition of these two numbers, and the addition of these two numbers is nothing but A. So, that shows that every common divisor of A comma B is also a common divisor of B comma R, and hence the greatest common divisor of A comma B will be the same as the greatest common divisor of B comma R as well. So, based on this observation, this is a very simple Euclid's algorithm. Your input pair is A comma B, where A is greater than B, and the idea is that in each iteration we will use this rule to reduce the magnitude of our A and B till we reach a point where R becomes 0. Okay. So, what we do is we start with x equal to A and y being B. So, x and y will be my placeholders, and my value of x and y will keep on changing. Okay. So, the placeholder occupies the value A and B to begin with, and I will iteratively keep on changing the value of x and y till I reach a stage where my y becomes 0. Okay. So, as I said that I will be using this lemma again and again. So, what I will do is I will find my R, which is my current x modulo y, and whatever is my current y that goes and becomes next x, and whatever the R that I obtain that will go and become the next y, and I keep on doing the process till my y becomes 0. When I reach a stage when my y becomes 0, then I return my x, and that will be my GCD. So, you can imagine that what is happening here is the following: you start and compute a sequence of remainders, and you stop when you obtain a remainder which is 0. So, I start with the given pair of values and treat them as the first remainder, 0th remainder and the first remainder respectively. Okay. So, imagine that R0 modulo R1 is R2, where R2 is a value in the range 0 to R1 minus 1, and then in the next iteration you will reverse the role of not reverse, you will update your x and y. So, this becomes x and this becomes y, and you obtain the next R, and then in the next iteration your R2 becomes your x and your R3 becomes y, and then you obtain the next remainder. Okay. And you keep on doing this process till you obtain a 0 remainder. The time when you obtain the 0 remainder, that means you have 0 here, you stop. Okay. And you will output R of n as the overall GCD. Now, what is the guarantee that this iteration will eventually terminate? What is the guarantee that this is not going to loop forever? The reason that it will eventually terminate is that in each iteration you are definitely reducing the value of your y by at least 1, okay, because you are now taking, you are updating the sequence of remainders. So, you start with the remainder with R naught and the other remainder being R 1, and in each iteration your remainders keep on getting decremented at least by 1. So, at most it will require a number of iterations to eventually obtain a remainder of 0. So, that means eventually the algorithm will terminate, and by applying this theorem I can say that the GCD of A and B is same as the GCD of the 0th remainder and the first remainder, and that is same as the GCD of, so you can treat this as A and B and this is your B and R, and then in the next iteration your role of A and B and R gets changed and so on, and when you obtain GCD of Rn comma 0, that means you obtain the other remainder being 0. So, the GCD of Rn and 0 will be of course R of n, and that is the overall GCD, because you can come back all the way and say that this Rn will be the GCD of A and B as well. Okay. So, the now next question is, what is the running time of the Euclid's GCD algorithm? Is it polynomial in the number of bits that I need to represent my A and B or not? Because that will be the our measurement of time complexity, and there is a very interesting result attributed to Lemis which says the following, and we will use this theorem to conclude that the Euclid's running time is polynomial in the number of bits that you need to represent your A and B. So, what Lemis theorem says is the following: if there are total n iterations used in your Euclid's GCD algorithm, then the value of B is same as the n plus 1th Fibonacci number. It is a very beautiful result which relates the number of divisions which are used in the GCD algorithm with the Fibonacci sequence. Okay. And the proof is as follows. We will give a direct proof. So, since we are assuming that there are total n iterations or equivalently n divisions which are performed. So, by the way, if you are wondering where exactly division is involved, this is the step where division is involved. Okay. So, basically we want to find out how many times this x modulo y operation will be performed in the Euclid's GCD algorithm. I do not want an algorithm where this x modulo y operation is performed exponential number of times. So, if n divisions are performed, so what I have done is I have listed down the various remainders which I will keep on getting in each updated iteration, and then in the nth iteration I obtain 0 remainder here, namely Rn minus 1 is completely divisible by R of n. Okay. So, my claim here, I will make now a series of claims, and using that I will conclude Lemis theorem. So, my claim is that each of these quotients q1, q2, qn minus 1 is at least 1, and that is a trivial fact, because they are at least 1 because at the first place we have used n divisions to get the output of the Euclid's algorithm. Okay. So, that means definitely R naught is not completely divisible by R 1, and we obtain some remainder, because then only we have gone to the second iteration. So, that means q 1 is at least 1. Similarly, R 1 is not completely divisible by R 2, there was some remainder, that means q 2 is at least 1, and so on. The second claim is that the last quotient here q 1 is at least 2, and this is because q n is the ratio of n minus 1th remainder and nth remainder, and I know that n minus 1th remainder is strictly greater than the nth remainder, okay, because in each iteration x is strictly greater than y. So, since my and now if my quotient has to be an integer value, okay. So, I have numerator greater than denominator, and I know that this ratio this fraction q n r n over r n minus 1 over r n has to be an integer value. So, that means the minimum value of q n is at least 2. Now, based on these two facts, let us derive the proof for Lemis theorem. So, I can say that the nth remainder where I stop the algorithm is greater than equal to 1, right. It is not 0, it is greater than equal to 1, and if you see the Fibonacci sequence, the first term is 0, the next term namely f of 2 is 1, the next term is the summation of the previous two terms which is f of 3, the next term is the summation of these two terms which will be 2, and so on. So, I can say that R of n, the last remainder, is at least the second Fibonacci number. Now, what about the previous remainder? So, the previous remainder R n minus 1 is q n times R of n. Now, I already know that R n is greater than equal to 1 and I also know that q n is at least 2. So, this is an exact equality, but I know that R n is individually greater than equal to 1 this value and q n is individually greater than equal to 2 and R n definitely will be now at least 2 times R of n and 2 times R of n is nothing but I have already proved that it is greater than equal to f 2. So, I obtain that the n minus 1th remainder is as large as 2 times f of 2 and if you now compare it with the Fibonacci series here, this value is nothing but greater than equal to f 3. Now, I go to the previous remainder. So, remember my goal is to say something about B, that is what the Lem's theorem is. So, what I am saying is I am going backward and trying to find out an inequality relating all the remainders and then I will finally stop with R of 1 which is the value of B. So, in the same way I can say that the n minus 2th remainder, its exact value is this. I know that q of n minus 1 is at least 1 and I already now have a relation or inequality involving R of n minus 1 and hence I can say that R of n minus 2 is greater than equal to this. Okay. So, I can substitute q n minus 1 greater than equal to 1 and then I can substitute this inequality for R of n minus 1 and hence I conclude that R of n minus 2 is greater than equal to f 4. And now, if I keep on doing this process, I can come to the conclusion that R of 2 is greater than equal to f of n and then finally, when I come to R of 1 which is the same as B and R of 1 is this value q times R 2 plus R 3, q 2 is greater than equal to 1. So, I can say B is greater than equal to R 2 plus R 3, but R 2 in the previous step I would have concluded is greater than equal to f of n and hence I can conclude that B is greater than equal to f n plus f n minus 1 which is same as the next Fibonacci number and that precisely is the claim. But Lem's theorem directly does not help me to tell what exactly is the number of divisions. Let us derive the exact number of divisions using the Lem's theorem. So, I am stating the Lem's theorem here. Now, let me recall a lower bound regarding the value of the Fibonacci number and relate it with the well known golden ratios. It is a well known lower bound that in the Fibonacci sequence, if you focus on the nth term, then it is greater than the golden ratio raised to power n minus 2, where the golden ratio alpha is 1 plus root 5 over 2 and this can be proved using strong induction. I am not going to do that. Now, based on this lower bound and Lem's theorem, I can derive the number of divisions that are required in the Euclid's algorithm. So, the theorem I can conclude that the Euclid's GCD algorithm will require at most these many number of divisions. So, I am deriving the answer in the base 10, but you can derive the answer to the base 2 as well, because remember our time complexity is in terms of n, where n is equal to the number of bits that you need to represent your value a and b. Okay. So, it will be basically log of b to the base 2. So, whatever argument I am giving here, it can be modified easily to get the answer in terms of log of b to the base 2 as well. So, let us prove this theorem statement. So, imagine that there are n modular divisions or n mod operations performed inside your Euclid's algorithm. Then as per the Lem's theorem, we know that the magnitude of b or the value of b is at least as large as the n plus 1th Fibonacci number. And now, if I apply the lower bound on f of n plus 1, I can relate it with the golden ratio. So, I get the conclusion that b is greater than alpha power n minus 1, and the value of alpha is 1 plus root 5 over 2. So, if I take log on both sides of these two equations to the base 10, you can take the log to the base 2 as well, and that will give you a different result, but more or less it will be same. So, if I take log to the base 10, I get this equation here, this relation. Okay. And now, I can use the fact that the log of golden ratio alpha to the base 10 is approximately 0.208, which is greater than 1 over 5. So, that is why I can write it as 1 over 5 here, and that shows that n is less than equal to 5 times log of b to the base 10. Okay, so, sorry for the confusion here, n I used here for the number of divisions, and I was continuously under the impression that n is also the number of bits used to represent the values a and b. So, let us use a different representation. So, let n be the n, capital N, denote the number of bits used to represent a and b. Okay. So, what I have derived here is the following. I have derived that the number of divisions that you perform is upper bounded by roughly the number of bits that you need to represent your value b. So, we have getting it in the base 10. So, log of b to the base 10 is not n, n will be something else, but whatever derivation we have done here, the step where we took the log of log to the base 10, if we do it with log to the base 2, that will give us the value of n in terms of the value of n somewhere. So, it will not be more than the number of bits, asymptotically it will not be more than the number of bits that you need to represent your integers a and b here. Okay. So, that means Euclid's algorithm is actually a polynomial time algorithm, polynomial in the number of bits that you need to represent your integers a and b. And that is a very remarkable fact, because at the time when Euclid invented his algorithm, there was no notion of time complexity, there was no notion of polynomial time complexity, exponential time complexity, and so on. So, without even worrying about how efficient it will be, Euclid gave us a very fantastic algorithm to compute GCD of two numbers whose running time is polynomial and which can be used in practice. So, that brings me to the end of today's lecture. These are the references used. Just to conclude, in this lecture we introduced prime numbers, we discussed the Naïve algorithm for checking whether a given input number is prime or not. Its running time is exponential, and we also discussed about Euclid's algorithm for computing the GCD, whose running time is polynomial in the number of bits that you need to represent your input values. Thank you.